I'm going to draw first a transverse wave, which is the most common one, and I'm going to graph it, how it looks to the eye. So we have here the x-axis and the y-axis in space, and you're looking at the wave, and it looks something like this. It goes up and down, up and down, up and down. It looks like a sine trigonometric function. And there are some names for the characteristics of this wave. So first you notice it has peaks and it has valleys. Those have their own names. So all of the peaks, the tops, are called crests. And all of the valleys, or bottoms, are called troughs. It's a really weird word that I'm not even sure I'm pronouncing correctly, but troughs. Now, more important than that is some characteristics called amplitude and wavelength. So amplitude means how high the wave rises and how low it goes. So that means if you take the center of the wave, the place where it's at 0, and you measure how much it grows upwards, that is the amplitude. And the amplitude is usually called A. So A is our amplitude. And it's given in meters. Right? So the amplitude upwards is the same as the amplitude downwards if you have the line in the middle. So you can either measure it upwards or you can measure it downwards like this. It's going to give you the same amplitude, but it's always positive. You never give the amplitude as something negative because it goes up and down, up and down. So that is the amplitude. And the wavelength measures how far apart each peak or each valley is, each crest and each trough. So you measure the wavelength from one bottom to the other bottom. And it's given by the Greek letter lambda. So lambda is going to be our wavelength, also in meters. You can measure it from any point to any point as long as they're like consecutive points. So either valley to valley, or you can measure it from crest to crest. This is also one wavelength, and it's exactly the same wavelength as this one. Or you can measure it, for example, if I choose a random point here, then I have to go to the same random point in the next oscillation. So one complete oscillation will give me right this point. So this is also a wavelength, right? So you can measure the wavelength wherever you want, but it's usually easier to measure it at the troughs or at the crests of the wave. Just it's easier visually for us. So wavelength, how far apart they are. Amplitude, how much up and down it goes. So now I'm going to draw the same concepts, but on a longitudinal wave. So this one was a transverse wave. Now I'm going to draw a longitudinal wave and do the same thing. So this one I'm going to draw it as a spring, but it could be air, it could be anything. But I just think it's easier to see it as a spring. So the way that I did it here is that it's expanded here and compressed here and expanded here. So instead of calling them troughs and crests, now we're going to call them compressions and expansions. So of course, compressions is where the spring is all compressed, so it would be this part over here. This is a compression. And when the wave is all elongated, when the spring is elongated, it's called an expansion. Some people call it a rarefaction. So I'm going to write it in parentheses. This is how I learned it, rarefaction. But now it's more common to call it expansion. So you can call it compression and expansion. And we can also identify the amplitude and the wavelength, but here it's a little bit more complicated. So the amplitude is how much each piece moves. What is the maximum distance it can move? So here the piece of string moved up and down. Here it's going to move forward and backward. But that just, they have to tell you, it's not easy to see it in the drawing. So maybe this piece of spring had moved all the way back here and will also move all the way forward here. So half of that, let's say this half is an amplitude, this half is another amplitude, because you always measure from the middle, how much it goes up, how much it goes down. So each of these is an amplitude. And the wavelength is the same as here. So here it was the distance between two troughs, two consecutive troughs. Here it's the distance between two consecutive expansions or two consecutive compressions. So we could measure from the middle of this expansion to the middle of this expansion. All of this would be the wavelength, right? So those would be the four things: crests and troughs, amplitude and wavelength, and here expansions, compressions, amplitude and wavelength. Most times you're going to see this example because this one is just confusing and harder to tell from looking at a drawing. And the final thing that I wanted to mention with these drawings is how a single point oscillates. So as I told you, the wave is moving forward. The wave is moving through this piece of string, and then it's going to be farther over there. And the same with the spring. But every piece of string has its own movement. So if, for example, I'm looking at this piece of string, if I grab my string and color a point of the string green, how is that point going to move? So this is a little bit confusing, but if you think about it, it's just like the person who's floating in the sea. The person and the point are just going to go up and down as the waves pass through them and leaving the point to just oscillate up and down. So this single point will oscillate up and down. Every single point that you grab, it's going to oscillate up and down. And how do they move here? Well, this was perpendicular because it's a transverse wave, and here it's parallel to the direction of motion. So this whole circle of the spring is going to oscillate forward and backward, right? Frequency. So you've heard this before. Frequency is how many times you see something in a period of time. So for waves, frequency is defined as how many oscillations, how many complete oscillations there are in 1 second, so per second. So number of oscillations per second. And and there's something else called the period. So period talks about time. Period is in how many seconds an oscillation takes. So this is 1 second, how many oscillations, and this one is in one oscillation, how many seconds have passed. So this is seconds per oscillation, how long it takes. So these two are actually opposites of one another. So this one is called F, and this one is called big T because it's a time. Period is a time, it's given in seconds, so it's called big T. So an equation to relate them to, them both, is frequency is 1 over period. And if you want to solve for period, you're going to get period is 1 over frequency. So they're the inverse one of the other, because one is oscillations per second, the other one is seconds per oscillation. So the units, period is in seconds, of course, because it's defined as the seconds per oscillation, and frequency is in 1 over second. 1 over second, but it's so common to use that it has its own name. 1 over second is called hertz, and the unit is given as H, capital H, and lowercase z, hertz. So you've heard this, megahertz, kilohertz. When you're listening to the radio, they're talking about the frequency of oscillation of the radio wave that you're getting. You're going to have to use these two equations and with these units. And I also wanted to talk about speed and energy. Those are the only two things we're missing. So now I'm going to erase this one. Speed is called V, speed of the wave, and it's how many meters the wave travels per second. So of course our unit is, as always, the unit of speed, meters per second. Meters per second, that's our unit. And we can actually relate speed with wavelength and period. So another equation that is going to be very helpful today is this one. Speed is equal to wavelength times frequency. Of course, you can also solve for it and get, wavelength is speed over frequency, and frequency is speed over wavelength. These are just two forms of the same equation. This can help us maybe figure out the frequency and the wavelength of electromagnetic waves or sound waves. So electromagnetic waves we're going to see in a couple of classes all have the same speed, which is called the speed of light. Maybe you've heard it. It's the highest possible speed that anything can have in the universe. Light is the fastest thing in the universe, and it has its speed that we call c. C is the speed of light, and it's 3 times 10 to the 8 meters per second. Maybe you've heard it as 300,000 kilometers per second. It's the same thing. And the speed of sound is also a pretty common value. Speed of sound is 343 meters per second when sound is traveling in air. If it travels in water or something else, it's going to have a different speed. But this is the speed of sound in air, 343 meters per second. So if you know these values, and you always know them because they are just true for the whole universe, you can use this equation. And if you know the wavelength, you can find out the frequency. If you know the frequency, you can find out the wavelength. So the way this would look with light is c, the speed of light, is equal to the wavelength times the frequency. And with sound, the speed of sound is equal to the wavelength times the frequency. So if a question asks you about a radio wave or some type of electromagnetic or light wave, and they only give you the frequency and they're asking for the wavelength, you know that you also have the speed because it's always the same speed. Okay, that's about speed. And the final thing is the energy of the wave. So when I said the definition for waves, one of the most important things that the definition says is that that disturbance, that wave, carries energy from one place to another as it moves. So this is one of the most important things. But how much energy? So energy, which is E as always. We don't need to know an equation, there is one. Maybe we'll look at it in further classes, but right now the only thing I want you to know is that it's proportional to how big it is, how big it looks in the graph that I told you. So it's proportional to the size. So in the graph that I drew before, the energy is proportional to this area underneath, the area that is inside of the things. If you have a much bigger curve that looks something like this, then you're going to have much more energy because the energy is proportional to this whole size that is above and below the graph. So that's just the only thing you need to know about energy. The higher and lower it gets, the more energy. Frequency is also proportional, so if you have a wave of the same height, but it's a lot closer like this, the same amount has more wavelength, so it carries more energy. Okay, so that's it for the introduction to waves.